This video is on Newton's third law of action-reaction pairs. I'm Mrs. Estock. Let's get started. Let's begin this lecture by asking ourselves the following question. How does a rocket ship propel itself into space? A common misconception is that rockets have to push off against the ground in order to propel themselves into space, but that's not actually what's happening. With the physics of what's happening, you have the fuel that's pushing the rocket upward, not the ground. Because even when the rocket is in outer space, it can propel itself without a ground to push against. So truthfully, it's the fuel that pushes on the rocket. So the rocket doesn't actually need the ground at all. While the force of the fuel pushes the rocket upward, simultaneously the force of the rocket pushes the fuel out the bottom. So you have the fuel being pushed out of the bottom of the rocket, while the fuel pushes the rocket upward. This is what we call an action force and a reaction force. For every action force, there is a reaction force that is equal in size but opposite in direction. These two forces together are an action-reaction pair. Now, we can't do a rocket ship experiment in class, but we could use a simple idea like a balloon filled up with air being released. So when that balloon is released, there are two things happening simultaneously. The air pushes the balloon up, and the balloon pushes the air out the bottom downward. This is the action-reaction pair that allows the balloon to kind of, when you let go of a balloon, it does the thing and it goes all around the room, right? But that's not because it's pushing on anything outside of itself. It's the balloon pushing the air out the bottom. So this is what Newton meant with his third law: every action has an equal and opposite reaction. We can define this more in physics by talking about action-reaction forces. For every action force, there is a reaction force that is equal in size but opposite in direction. So in this sense, forces will always come in pairs. You cannot push on something without it pushing back on you. For example, if you push against a wall, that would be maybe the action force. The reaction force is the wall pushing back on you. That is Newton's third law. So which one happens first, the action or the reaction force? People tend to think that they happen at slightly different times, that the reaction force occurs slightly after the action force. But this is not actually true. They happen simultaneously at the same time. As soon as the action force begins to act on an object, the reaction force immediately begins to occur. For example, if you fire a gun, the action and the reaction forces will happen at the same time. So simultaneously, when you fire the bullet, let's call that the action force, the reaction would be the recoil of the gun. So while the gun pushes the bullet forward, the bullet pushes the gun backwards. And this happens at exactly the same time. There's no delay. They happen simultaneously. Another question I get asked about Newton's third law is how come, if every force has an equal and opposite reaction force, how come they don't just cancel out, right? Because if they're equal in size but opposite in direction, if we added them together like a net force, wouldn't the net force just be 0? That would be true, except for one major point. The action and reaction forces always act on different objects. If the two forces were felt by the same object, they would cancel, and the net force would be 0. But they happen on two different objects, and we would draw them as two different free body diagrams. Let's say the action force is the force of object A on object B. The reaction force would be the force of object B on object A. So one force is felt by object A, the other force is felt by object B. And because it's on two different objects, they do not cancel. Here's a diagram depicting what we just mentioned. So in this scenario, object A feels a force from B at the same time as object B feels a force from A, so that they are equal in size but opposite in direction. The last point we'll make about Newton's third law is the resulting accelerations. So one of the reasons people think that forces are not equal according to Newton's third law is because different massed objects experience different accelerations. But that does not mean that they experience different size forces. Let me explain using the following example. Let's say that you fire a cannonball from a cannon. Well, in this case, the action-reaction pair, according to Newton's third law, would be this. The cannonball feels a force from the cannon on the ball, and simultaneously the cannon recoils because the ball pushes the cannon backward. So this is our action-reaction pair. Equal in size, opposite in direction, felt by two different objects. The cannon feels a force pushing it backward, while the cannonball, feels a force pushing it forward. Well, we know from Newton's third law that these forces are the same size, but how can that be? Because the cannonball gets fired across the battlefield, while the cannon may only recoil a little distance, comparatively. So why is that? Well, we can explain it with equal forces, given that the two objects have very different masses. The cannon is much more massive than the cannonball. Therefore, the cannon has much more inertia and more of a tendency to resist a change in its motion. That's why they have different accelerations. The object with less mass gets accelerated more. The object with more mass gets accelerated less. Remember, we did an entire lab on this in class with the smart carts using pulleys. Given a constant force or the same size force, when we added mass to the cart, it caused the acceleration to decrease. So we're seeing an inverse relationship here between mass and acceleration. And that's what causes the different accelerations in the two objects, even though they are experiencing the same size force. Lastly, we'll go over one practice question. This is an example of the type of question you might see on the Regents exam. Typically, they like to throw a bunch of numbers at you and see if you can pick out what is the action-reaction pair. Here, Monkey Joe has a weight of 500 newtons, and he pushes with a force of 3,000 newtons on a 15,000 newton car and causes it to accelerate at 0.25 meters per second squared. What is the force of the car on Monkey Joe? In this case, the only way to solve this is by Newton's third law. We have to find the action-reaction pair. So if we're looking for the force of the car on Monkey Joe, we have to figure out which one of those forces listed is the force of Monkey Joe on the car. In other words, how much force is Monkey Joe applying to the car? Well, if we read through the question, we can see the applied force is him pushing the car with 3,000 newtons of force. So that means the force of the car on Monkey Joe would be the same size, but in the opposite direction. So we could say mathematically, the opposite direction would be negative, but the same magnitude, 3,000 newtons. That's it for Newton's third law. Thanks for watching.